what I'm attempting or what I'm studying here is the effects of different propeller shapes on the efficiency of propeller designs. And in order to do that, I built a computer-controlled homemade apparatus that derives efficiency from wattage input and wattage output. Basically, all you do is, after you're done calculating wattage input, which is voltage times amperage, you divide that by the centrifugal force multiplied times the velocity, which is actually equal to mass times velocity squared divided by the radius at the center of gravity times velocity once again. And you'll end up with the actual wattage used by the propeller on the surrounding air, or the amount of power used by the propeller on the surrounding air. And then you just divide that number by the wattage input used by the motor, and you end up with an efficiency. The propeller that's on there now has an efficiency of around 35%. So that means the power from the actual transformer and DC power supply is reduced about 60% by the time it actually reaches the propeller. And 35% is really not that bad, considering that turbines run at about 40% efficiency and piston engines run at about 28% efficiency. I believe that number one was the most efficient because of the RPM range that I was using, which was between 1 and 2400 RPMs or RPM, and that's around the normal operating range for piston engine or turboprop aircraft of today. And if you look at those are definitely not rectangular, but the theory is similar. Those propellers are specifically designed to have the same amount of lift across the entire area of the blade, so that the inside or the root of the propeller is actually at a higher angle of pitch than the outside of the propeller or the tip of the propeller, and therefore you get an equal amount of thrust or lift across the entire blade, because the inside of the propeller rotates at a slower acceleration than the outside of the propeller. So the added angle of pitch on the inside actually helps to produce an equal amount of lift. Last year I was testing the amount of thrust that different propellers produce, and that's decent, but efficiency is much more important, because you can say I own a Corvette that has 400 horsepower and definitely going to go very fast, but you only get 5 miles per gallon. And when you're talking business, you want more for less. So what you want to do is design a propeller that produces a lot of thrust, but with very little power needed from the engine or the motor. And with the help of composite fibers, which I used, I actually took a core of basswood, which is just the base design, and then I coated that with a carbon fiber cloth and also a nylon mesh cloth, and super glued that, and then added a coat of a monocoat sealer over the top, so it's nice, black, and slick. And the propeller, which is on the prop right now, was the most efficient, which was actually, last year I came out with a different shape for the most thrust, but this was the overall most efficient. And this laptop controls the entire apparatus. I have my digital voltmeters and ammeters. Those are basically what give you the wattage. I have a phototransistor infrared switch, which measures the RPM in milliseconds or in microseconds, so the computer receives the microsecond count of the time duration between each rotation of the propeller, and then converts that to RPM. The angle of pitch is controlled by a radio-controlled car servo, which is then attached to a radio-controlled helicopter tow rotor and swash plate assembly, and that controls the angle of pitch. Then the servo is also attached to a potentiometer, which gives a relative voltage count whenever the servo adjusts. Therefore, you can set a certain angle or a certain position on the servo. You can assign that a certain voltage value. So when you program into the computer, you can simply tell it to adjust until the potentiometer is reading at a certain voltage, and that would be equal to 5, 10, or 15 degrees of pitch, whichever one you assign. It also controls the varying speed of the propeller. I basically have behind there two stepper motors, which are attached to digital to analog converters, which then power the servo and the speed controller. Now the speed controller is powered off a 10-volt unregulated analog supply. I run the propeller at between 1,000 and 2,400 RPM, and I specifically programmed the computer to produce the rotating motion on the propeller to begin the program, then adjust the angle of pitch. When the pitch is adjusted, that actually causes drag on the propeller, so the RPM is reduced, and then I also issue a command in the program once the angle of pitch has been adjusted to readjust the RPM to make sure that it's rotating at 1,000 or whichever one I specify. And then I plug in. I have the equations plugged into the computer. It will automatically derive the efficiency, the wattage, and the thrust produced from the digital scale I have attached to the arm with a mechanical advantage already programmed into the computer. Yeah, the entire thing I built by hand with a 1975 Craftsman drill and a hacksaw and a couple screwdrivers. It's taken me about a year, and it's definitely been a great learning experience. I've probably learned a lot more from this project in the means of troubleshooting than I have from my science classes the 4 years I've been in high school. So it's definitely been a very good thing to work with. It's helped me a lot. Okay, now what I'm running here is the actual calibration program. The program I have written for this, I have specifically designed to print data out on a printer, and therefore, since I don't have the printer attached, it's going to lock up. I'm working on a program currently to actually store the data in a file on the disk so that I don't have to use paper at all. It'd be a completely green project. Okay, what I'm going to do now is issue a command to the computer interface, which will adjust the pitch on the prop. Now what I'm going to do is reverse that so it goes back to 0 degrees of pitch. Display of how it actually rotates and when we're running. If you will pay attention to the voltage and the ammeters, you will see those register. Adjusting the speed up and down while it's rotating. And I can also adjust the angle of pitch on the propeller on the fly with the swash plate. There we go. And you'll see it jump forward a tad bit. Producing a little bit of thrust. And all I'm going to do is issue a voltage measurement to the potentiometer, see at what angle it's at. Now it's at about 10 degrees of pitch. And we can find out what RPM it's rotating at. It's rotating at about 40,130 microseconds, and you convert that 1 over 40,130 microseconds multiplied by a million, multiplied 60 to get RPM, and I don't know if anybody has a calculator on my note, but I'd wager to say it's probably around 3,500 RPM. Funding was basically derived from my work over the summer, working for a computer networking company, and also Mom, who donated several $100s to me. This actual project here cost, without the laptop, $1,230 to build. With a laptop, probably close to about a little over 2,000.